Okay, let's unpack this. Um, have you ever stared at a mountain of data in your code, wishing there was just a simpler, maybe faster, more elegant way to handle it? Without writing lines and lines of boilerplate.
Right. That feeling is pretty common.
Well, today we're doing a deep dive into Java streams. And our mission really is to cut through the jargon, pull out the most important nuggets, and make sure you walk away feeling genuinely clued in about this really powerful feature.
Yeah, what's fascinating about streams, which landed with Java 8, is they weren't just some minor addition. It felt like a fundamental shift.
Or shift how?
They brought this functional programming style right into Java, which, fundamentally reshaped how developers actually think about and process data. It was a bit of a paradigm leap, really.
Okay, so let's start right at the basics then. What are Java streams, fundamentally?
Well, the first thing to grasp, and it's crucial, is that a stream is not like a list or a set.
Okay.
It doesn't store elements.
Okay. Not a data structure in that sense.
Exactly. Think of it more like a pipeline, a conduit for processing data from a source. That source could be a collection, maybe an array, even an I/O channel.
I like the analogy in the source material like a conveyor belt. Data flows along, it gets processed at different stations.
Right. Filtering, transforming, sorting,
Hmm.
whatever steps you define. And it flows towards a final result. Critically, though, it does all this without messing with the original data source. That stays untouched.
That non-modification aspect sounds important.
It is. And this whole pipeline idea enables something called declarative programming.
Declarative. Okay.
Yeah.
Break that down a bit.
It means instead of you telling the computer how to do something step by step, like, writing out intricate loops, you just declare what you want.
Like, give me all the numbers bigger than 10.
Precisely. You state the goal, the how, the mechanics of iterating and filtering. That's handled by the Stream API itself. And often it can do it much more efficiently because it sees the whole pipeline. It kind of shifts the burden.
That makes sense.
Yeah.
So you build this pipeline, this conveyor belt. What kinds of tools or stations can you put on it?
Good question. There are basically two main types of operations you use with streams. First, you've got intermediate operations.
Yeah, okay.
These are the processing stations. They transform or filter the stream. Things like filter, map for transforming elements, sorted. You get the idea.
Right. Standard data manipulation tasks.
Exactly. But the really clever part about these intermediate operations is that they are lazy.
Lazy? How so?
It means they don't actually run right away when you define them. They just build up the plan, the blueprint for the pipeline. Nothing actually happens.
Until you ask for the final output.
Precisely. It's like setting up a whole chain reaction, but you don't push the first domino until you're ready for the end result.
I like that. So what does push that first domino?
That would be the terminal operations. These are the ones that actually produce a result or maybe a side effect. Things like collect, maybe gathering the results into a new list.
Or for each. Like doing something with each item.
Exactly. For each is a common one. Or reduce, where you combine all the elements into a single value, like a sum or a max. It's the terminal operation that says, okay, go, and triggers the computation for that entire lazy pipeline you've built.
And that laziness you mentioned, it helps with optimization.
Oh, absolutely. It's a huge potential performance win because the JVM knows the entire sequence of operations before it starts. It can sometimes fuse operations together or find other shortcuts. It sees the whole picture.
Okay, right. This is where it gets really interesting, I think. The part that makes developers genuinely excited. We know what streams are, sort of fundamentally. But the big question is why? Why are they such a game changer? Why should you, listening now, really care?
Well, the reasons are pretty compelling, actually. First, there's that declarative programming aspect we touched on. It's more than just cleaner code. It's freeing yourself from the nitty-gritty, how to focus purely on the what.
Describe the result, not the process.
Exactly. And that naturally leads to much simplified data processing. A task like finding all the even numbers in a list and then sorting them. Used to be several lines of code, maybe temporary lists.
Right, loops, conditional checks,
Yeah.
adding to a new list.
Yeah. With streams, that can often be a single, fluent line of code. It reads much more closely to how you describe the problem.
And then there's the parallel aspect, right? That seems huge.
Oh, definitely. Parallel processing. Streams have built-in support for it. You can basically tell a stream, hey, run this pipeline in parallel, and it can automatically leverage the multiple cores on your processor.
Without you having to write all the complicated and frankly error-prone threading code yourself.
Exactly. That's a massive advantage, especially when you're dealing with large data sets. The performance gains can be significant.
Wow. Okay. What else?
Well, you can easily chain operations. You can link, filter, then map, then sort, whatever you need into this single, quite modular pipeline.
Which sounds like it would help with keeping things organized and readable.
Absolutely. Which leads to improved maintainability. Stream-based code tends to be shorter, expresses the intent more clearly. That usually means fewer bugs down the line and makes it easier for teams to collaborate on the code.
So connecting this to real-world stuff.
Yeah, if you think about the bigger picture, streams are just making common tasks way easier and cleaner. Selecting specific records from a database, that's basically filtering, converting data from one format to another. That's transformation, like map, calculating sums, averages, aggregation, like reduce,
So it takes these common data patterns.
and gives you an elegant, efficient, and very readable way to express them in Java. It simplifies complexity.
Okay, let's really focus on that contrast for a moment, the aha moment. For years, like you said, Java developers, if they needed to process a collection, they reached for a loop. A for loop, maybe an enhanced for loop, or an iterator.
Right, that was the standard toolkit.
But then streams came along. How did they fundamentally change that old way of doing things? Let's compare them directly.
Okay. The most obvious difference, I think, is conciseness and readability. Streams just slash the amount of boilerplate code. Filtering a list in a loop means initializing a new list, writing the loop structure, the if condition, the add call.
Whereas with a stream,
It's often list.stream.filterCondition.collect, collectors.toNeolist, one line. Your intent is just right there, super clear.
and it encourages a different style of programming too, right?
Yeah.
You mentioned functional.
Yes, the functional approach. Stream operations are generally designed to be stateless and avoid side effects.
Okay, let's quickly clarify those terms again, stateless and side effects, just to be sure everyone's following.
Sure. Stateless basically means the operation's result depends only on its input. It doesn't rely on any state that might have changed from processing previous elements. Each element is handled independently.
Got it. And side effects.
That means the operation doesn't change anything outside of itself. It won't modify the original list. It won't change some global variable. It just produces its output. This makes the code much more predictable, especially, again, when you think about running things in parallel.
Right. No unexpected modifications happening elsewhere. So we have conciseness, readability, this cleaner functional style.
And don't forget lazy evaluation. We mentioned it, but it's a core difference from loops. Loops process eagerly. Streams wait. This avoids doing work if the final result doesn't actually require it. Imagine filtering a huge list and only needing the first element. A stream might stop processing much earlier than a loop.
Potential performance win again.
Definitely. And parallelization, as we said. Just adding parallel stream instead of stream can unlock multi-core processing. Trying to manually parallelize a complex loop is, well, it's hard and full of pitfalls.
Yeah, I can imagine. Race conditions, deadlocks, not fun.
Exactly. Streams handle a lot of that complexity for you. Plus, you get great flexibility from combining all the different operations and overall pipeline efficiency because data often flows through in a single pass, optimized by the JVM.
Let's use that concrete example from the source again. Finding names starting with A, uppercasing them, sorting them.
Right. With loops, that's probably 3 distinct steps. Filter into a new list, iterate that list to uppercase into another list, then sort the final list. Lots of intermediate stuff.
And with streams.
It's one chain, .names, .stream, .filter, say nnas, men, starts with a.map, string .to uppercase, .sorted, .collect, collectors, .toList. Boom, single pipeline, clear logic. It reads like the problem description.
It really does shift how you think, doesn't it? From do this, then do that, then do this other thing, to here's the sequence of transformations I want.
Absolutely. Thinking in terms of these pipelines rather than just sequential steps, it encourages a more, I'd say, elegant and often more efficient way to design your solutions from the get-go. It's a mindset shift.
Okay, so we've seen the elegance from the outside, but let's pull back the curtain now. How does this actually work? What's Java doing under the hood when you chain filter.map.collect?
Right, the internal mechanics. Fundamentally, any stream operation has 3 stages. You've got the source, where the data comes from, the list, the array, whatever.
Step 1, get the data.
Yep. Step 2, define the intermediate operations. That's your filter, your map, your sorted. But remember, these are lazy. They're just recorded, building up that execution plan. Nothing runs yet.
Just building the blueprint.
Exactly. And step 3 is the terminal operation. That's your collect, for each, reduce. That's the trigger. That's what says, okay, execute the plan now, and produces the final result.
And that lazy evaluation is absolutely central to how it optimizes things, right?
Totally central. Because nothing runs until that terminal operation is hit, the Java virtual machine, the JVM, can look at the entire pipeline. It might realize, oh, I can fuse these two map operations, or I can perform this filter more efficiently. It avoids creating lots of intermediate collections and minimizes passes over the data.
Clever. Is there anything else important happening internally?
Well, yeah, there's a component called the splitterator.
Splitterator. Sounds fancy.
It does, but it's just short for splittable iterator. Its job is basically to traverse the data source and, crucially, to split it into chunks. This splitting capability is what makes parallel processing efficient.
Ah, so it helps break the data up for parallel work.
Exactly. When you use parallel streams, the splitterator divides the data, and then Java's fork join framework kicks in.
Fork join.
Yeah, that's Java's built-in mechanism for handling tasks recursively, breaking them into smaller subtasks that can run on different processor cores, and then combining the results. So the data gets chunked, processed concurrently via fork join, and the results are merged back together.
All managed automatically when you just ask for a parallel stream.
Pretty much, yes. And one other crucial internal aspect is immutability. We mentioned streams don't modify the source. That's key. They operate on the data flowing through, producing new streams or new collections as output. This guarantees data integrity and makes reasoning about the code, especially parallel code, much safer.
Understanding that internal flow source, lazy intermediate ops, terminal trigger, splitterator, fork join for parallel seems pretty important for using them well.
It really is. Knowing how it works helps you leverage its power effectively and helps you avoid some common misunderstandings or pitfalls.
Okay, so you have pitfalls. Streams sound amazing, incredibly powerful. But usually there's a catch, right? They can't be the perfect solution for everything. What are the nuances, the things you need to watch out for?
That's a very fair point. They aren't a silver bullet. First off, there's definitely a learning curve.
For sure. Functional concepts can be tricky at first.
Right. If you're steeped in traditional imperative loops, thinking in terms of map, filter, reduce, and especially understanding laziness, it takes a bit of adjustment. It's a different way of thinking.
And performance. They're not always faster.
Correct. For very small data sets, the overhead of setting up the stream pipeline can actually make them slightly slower than a simple traditional loop.
Interesting. So they really shine with larger data sets.
Generally, yes. Or when you have complex chains of operations where the optimization potential pays off. Or, of course, when parallelization gives you a big boost.
And what about parallel streams themselves? Any catches there?
Yeah. While powerful, parallel stream challenges exist. They aren't guaranteed to be faster. For small tasks, the overhead of splitting and merging might outweigh the concurrent execution benefits. And more importantly, if the operations you're performing aren't truly stateless or thread safe, you can introduce subtle bugs like race conditions. You have to be careful that your Lambda expressions don't have side effects or rely on shared mutable state when going parallel.
Okay, that's a big one. What else?
A really critical point, especially for beginners, is limited reusability. A stream pipeline can only be consumed or traversed once.
Once. Meaning after a terminal operation, it's done.
Exactly. If you try to call another terminal operation on the same stream instance, you'll get an illegal state exception. You have to go back to the original source and create a new stream if you want to process the data again.
Ah, okay. That's easy to trip over if you don't know it.
Very common mistake. Also, some find debugging difficulty can be an issue.
Yeah, I've heard that. Why is that?
Mostly because of the laziness. When you step through with a debugger, the intermediate operations haven't run yet, so it's harder to inspect the data at those intermediate stages compared to stepping through a loop where state changes line by line. You need slightly different debugging techniques.
Like maybe using peak or collecting intermediate results.
Exactly. Peak is designed for this kind of debugging, or sometimes you might temporarily add a collect step. It just requires adapting your approach. And finally, streams are not ideal for all tasks. They excel at processing sequences of data. But if your logic involves, say, complex control flow, like needing to break out of a loop early based on some condition, or if you need to frequently modify the underlying collection while iterating, a traditional loop might still be clearer or more appropriate.
So pulling that together for someone starting out, what's the key advice?
I'd say start simple. Get comfortable with filter, map, collect. Really try to internalize the lazy evaluation. Nothing happens till the terminal up. Focus hard on writing stateless lambdas with no side effects, especially if you plan to use parallel streams later.
And that reusability thing.
Remember, one stream, one terminal operation. Always get a fresh stream from the source, practice thinking functionally, and, if performance is critical for a specific piece of code, don't just assume streams are faster, test it. Benchmark it against a loop for your specific use case.
Sound advice. Okay, so this has been a fantastic deep dive. We've seen the immense value Java streams bring, that conciseness, the readability, the powerful data processing, especially with parallel capabilities. They really did change the game for Java developers.
Absolutely.
But we've also highlighted those important nuances: the learning curve, performance considerations, the one-time use, debugging things you need to keep in mind to use them effectively.
Right. And this exploration of how streams leverage functional principles in Java, it kind of leads to a broader thought, doesn't it? If we connect this to the bigger picture, it really raises an important question for you, the listener.
Which is?
Beyond just Java streams, how might these functional programming ideas, immutability, statelessness, declarative pipelines continue to evolve? How might they reshape the future of how we as developers interact with and process data across all languages and platforms? It's a trend worth watching.
That's a great final thought. It's not just about Java 8 anymore. It's about a fundamental shift in programming paradigms. We definitely encourage you to go out, explore, experiment with Java streams, and apply some of these insights. Thanks for joining us on this deep dive.